Hi, this is Matt McCormick. I'm in the Department of Philosophy at California State University, Sacramento. My email address is mccormick@csus.edu. This is my fourth and last Introduction to Bayes Theorem lecture for my Inductive Logic Phil 61 course. We've been going back and forth by looking at and trying to understand try to understand what Bayes theorem is, and then doing problems, and then going back to the concepts in the English, and then doing more problems and trying to understand what it allows us to do. And we have learned and seen how a Bayes theorem lets us accurately um, revise our beliefs in the light of new information. So when you assign a probability to some belief you already have, and you get some new piece of information, and it has a probability of being true or a likelihood, Bayes' theorem lets us fold those together to then understand the relationship of how the information might lead us to come to believe the conclusion more or less. You get some more information about some murder suspect that leads you to think that they did it even more than you did before, or you get some medical diagnostic test result that tells you that you do have a disease or you don't have a disease. These are all probabilities, they're all inductive cases, and we're always trying to understand how to fold these uncertainties together. So now we're going to consider some more advanced and tricky Bayes problems, more advanced ideas connected to Bayes' theorem. So we're going to talk about how to solve for the prior or the base rate to work backwards in some of these problems. We're going to talk about solving for three mutually exclusive hypotheses. We're going to talk about solving for the likelihood and incorporating multiple tests for more certainty. Now that's my plan for this lecture today. So here's a new kind of problem. Suppose you work for quality control at a company, checking the gadgets that come off of the assembly line. You use a tester for flawed gadgets and randomly test a gadget from the line. Your tester says that it's flawed with an 88% accuracy. That is, the posterior probability that the gadget is flawed, given that the tester says it's flawed, is 0.88. Notice the way I just said that sentence. You know your tester is 95% accurate, that's the likelihood, from other analyses. What is the prior probability of flawed gadgets on the assembly line? That is, what rate of gadgets are flawed? And so we're trying to figure out the prior. We're making an observation. We've got an instrument or a testing tool that we know how good it is. It gives us an answer, that's the posterior probability, and we're going to try to work backwards from all of that to figure out what's the prior. Why do we want to know the prior? Well, imagine that you're operating with a big population of whatever, gadgets or motors or people or diseases or whatever, and you can't access or you don't know what the base rate in the population is. So if you do have some other information, you can use that, your test, your likelihood, your posterior probability to leverage your information and go backwards to work out the answer to the question. So part of this is just recognizing what's being asked for. This problem gives us the posterior probability, it gives us the likelihood, and then it asks us to determine the prior. And it's very important to recognize that that's what's being asked for, which means we set it up like this. So here's our numbers. The posterior is 0.88. The accuracy of our test is 0.95. And we're trying to figure out the prior or the base rate, which is x in my equation up here. Now, why did I use 1 minus x in the bottom? Because if you'll recall, I don't have it written out here, but you'll recall from the Bayes theorem for two mutually exclusive hypotheses, that bottom right parentheses for the denominator is the probability that the hypothesis is not true, which is the prior subtracted from 1. That is, the prior plus the probability the hypothesis is true plus the probability the hypothesis is not true should add up to 1. So these two numbers, x and 1 minus x, give us the full range. So we substitute those in, x, and now we're just going to use some simple algebra to solve this problem. The posterior is 0.88, the likelihood is 0.95. We're trying to solve for the base rate, and the value for not h in the denominator will be 1 minus x for two mutually exclusive hypotheses. So now we're just going to solve for x. So we first multiply in the denominator from above and combine like terms. So at the top, we've got a complicated denominator. Go ahead and multiply that 0.05 times 1 minus x, and then combine the like terms, and we get this new denominator. Now, to get rid of that fraction, we multiply both sides of the denominator to get rid of the fraction. So now what we're trying to do is to get x isolated on one side of the equal sign and get a number on the other. We're trying to solve for x. So now I've gotten rid of the fraction. I can multiply the left-hand side, multiply that 0.88 by both things in the parentheses, and I get 0.792x plus 0.044 equals 0.95x. And now I can subtract 0.792x from both sides, and I'm left with this equation. And now I've almost got x isolated to where I can solve. I divide both sides by 0.158, and I get an answer. X equals 0.2784. That's the answer to this question. What's the prior base rate of gadgets being flawed from the factory? I just walked into the factory and I just grabbed one off of the assembly line and I tested it. And I got an answer, and now I can use that piece of information to figure out about the whole factory that it actually has. It's a really shitty factory. 28% of the gadgets that they produce are flawed. But I did that with my one piece of information by working backward and solving for the prior. And this is very similar to the way we did this for conditional probability, but now things are more complicated because Bayes' theorem has got that much more complicated denominator especially. Okay, so now what about solving Bayes for 3 mutually exclusive hypotheses? We've always looked at 2 mutually exclusive hypotheses, but it's actually an easy matter to solve for 3. It works the very same way. And here's a problem that I just made up. I'd get sued by these rock climbing companies if they found out that I made this problem up, because these numbers are awful. Camming units for rock climbing are made either by Black Diamond, 62% of them come from Black Diamond, 18% come from Wild Country, and 20% come from Metolius, equipment companies. The Black Diamond cams have a 5% failure rate. That's the really bad number. Black Diamond would never allow that. Wild Country failure rate is 3%, and Metolius units have an 8% failure rate. Okay, so we test a camming unit chosen at random, and it fails. What's the probability that it came from Metolius? Okay, so part of this is just understanding how to set the problem up. Before, we did it with 2 mutually exclusive hypotheses, and we had those 2 conjuncts on the denominator. Now it's just going to have 3 conjuncts on the denominator. It's going to work the very same way. So for 3 mutually exclusive hypotheses, here's the problem. What's the probability that the cam came from Metolius given that it failed? It's the probability that it failed given that it's from Metolius times the probability of it came from Metolius over this first conjunct is the same as the numerator. The second one is the conjunct that's for Black Diamond. And the third conjunct is for the Wild Country camming units. These 3 conjuncts represent all of the 3 kinds of camming units and all the ways they can fail. So before we just considered for the hypothesis being true and the hypothesis being false. And now we're considering for the hypothesis being true or one of 2 other hypotheses being true. So it just becomes a slightly more complicated denominator, but otherwise the format of it's the same. So when we plug these numbers in now, we get 0.08 times 0.2, and we plug in the values from the problem into the equation, and we solve all of that, and we get 0.3. Okay, so what did we answer? What's the probability? So what I did is I grabbed, let's see, we test a camming unit chosen at random. So presumably it came from one of these 3 companies at those rates. I grab one of them, I test it, and it fails. Okay, so I'm trying to figure out, did it come from Metolius? This says that the answer, that the probability it came from Metolius is only 30%. So I'm not going to do it here, but what you do next is that's only 30%, but we might want to know, well, which company did it come from? and I need to find out which one it came from with a higher probability. I mean, maybe maybe the other one's zero point 0.4 and maybe the other one is 0.3, which would make for a total of 1. But we might want to explore and figure out what the most probable one is. One question we might want to answer is, which company did it come from? In which case we would run this same equation, but instead of doing Metolius on the numerator, we would do Black Diamond on the numerator. Very same equation. We just take this 0.05 times 0.62 and move it to the numerator, or double it, and copy it up there, and then solve. And then likewise, if we wanted to solve what's the probability it came from wild country, we would take this number, these two numbers multiplied together, and copy them and put them on the numerator and solve for that. We'd get 3 different probabilities down here, and then we'd be in a better position to say which one is it probably. I hope that makes some sense. It should, given some of the previous examples we did for conditional probability. Okay, next problem. I want to show how we can use multiple tests to keep revising the base rate and improving our information. And this is pretty simple and pretty straightforward given what we've done with conditional probability. So suppose Barbara's base rate for being pregnant is 25%, and then she takes a test that's 92% accurate and it tests positive. What's the probability she's pregnant? Okay, that's a straightforward Bayes problem. Suppose she takes another test after the first one. Now what's the probability that she's pregnant? Okay, so the way you do this is just you do it as 2 straightforward Bayes problems. The first one is just what's the probability she's pregnant given that she tested positive, and we do this the very same way we've done all the others. So we'd get this answer, 0.79. So when you plug in those numbers into this equation, we go from thinking Barbara's pregnant at 25% to now 79%. That's after one test. The question is, now what do we do if she takes another test? Okay, so here's the way to think about it. We've now incorporated a new piece of information, and so now we have a new prior. We have a new, the posterior probability of her being pregnant after that observation was 0.79. Now, were I to go and get a new piece of information and fold that into Bayes with this equation again, I'm going to use this as the new prior. This is now where we are with thinking Barbara's pregnant. We used to think she was 25% likely, probable to be pregnant. Now we think she's 79% given that she took one test. So what we do in the new equation for the second test is we put 0.79 right here, and that's the new base rate that changes from 0.25 from before. And then importantly, the probability that she's not pregnant changes to 0.21. In the original problem, the probability she wasn't pregnant was 75. Probability she was pregnant is 25. But now, with our first test result, it's now 79% probable that she's pregnant and 21% probable she's not. So now the second test answer comes out, not surprisingly, as 0.977. So Barbara's gone from 25 to 79 to 98% probable to be pregnant, where she didn't have a test, and then she did have a test positive, and then she tested positive again, and that information has been sequentially folded in and revised and given us new answers to the question, is she pregnant? So that's how you do multiple tests. You revise the base rate, you fold the new information in, and don't forget or don't miss this point here that the probability the hypothesis is not true changes here because now the probability of the hypothesis is higher, so this 0.21 is different than what we did in the first case. Okay, so now a harder example, another sort of problem. Let's suppose the probability that Matt has COVID, given that he just tested positive, is 0.32. Okay, so that's a posterior probability. I'm just going to give you that. Before the test, the probability that he had it was 0.01. What's the accuracy for that test that he took? So we could actually use information we have in a real diagnostic situation to try to figure out, well, how good is my test? If I know independently that somebody's got COVID or doesn't have it, or I know with what degree I believe it on the basis of the test, then I can work backwards again and solve for the likelihood. So now it's recognizing that we're trying to figure out what is the what is the likelihood? So it's this number right here, this x on the numerator of the equation. remembering that this is where we put the accuracy of the test in previous examples. So now we're just going to push that number through. Notice I used 1 minus x here to capture this is the false positive rate for the test. So if the accuracy of the test is x, then the inaccuracy of the test is going to be 1 minus x, just like the problems we've been doing in the past, where if a test is 99% accurate, then it's 0.01% chance it's going to give a false positive like it did in this case, or as it perhaps it did in this case. So now multiply through those numbers, get rid of the parentheses, combine like terms. I'll say that one more time more slowly. Multiply those in, get rid of the parentheses, and combine like terms. And I'm left with this equation from the first. And then multiply both sides by the denominator to get rid of the fraction. So now I multiply the left-hand side by 0.9 minus 0.8x, and the fraction goes away on the right-hand side. Multiply 0.32 into that parentheses on the left-hand side to get that equation. And now I can add 0.25x to both sides to get rid of, to get the x isolated on one side and get a number on the other. If you look at that, you'll see how that works. And then divide both sides by 0.356 and run the division, and we get 0.8. So what did we answer? We were trying to figure out how good is this test on the basis of the information we had. We had the posterior, we had the base rate, and we inserted a variable in for the likelihood of the test, and then solved for that variable. And we used 1 minus x to capture the false positive rate, and we get a 0.8. So what we determined then is that in this circumstance, the test is 80% accurate. Okay, so now we've done several more advanced, more difficult Bayes problems. We solved for all the different components of the test, or of the equation. So we solved for the prior, or the base rate. That's not the case we just did. That was the first case we did. We've solved for 3 mutually exclusive hypotheses, where one of 3 things is going to be true instead of one of 2. We solved for the likelihood. That's the kind of case we just did. And we also looked at examples where you incorporate multiple tests for more certainty, and you revise the base rate in the subsequent calculation of Bayes' theorem. So we've been primarily working with Bayes' theorem for 2 mutually exclusive hypotheses, and it's looked like this, and I've warned you that you need to memorize this and be able to reproduce this at will. And I used, in the last lecture, I used this nice quote from Steven Pinker to kind of explain it one more time in English. Here's what we've done. We've figured out that your credence in a hypothesis, the extent to which you should believe some new hypothesis after you've looked at the evidence, that's the posterior, should be your prior credence in the hypothesis. How much did you believe it beforehand? Multiplied by how likely the evidence would be if the hypothesis were true, that's that likelihood, scaled, there's the fraction, by how common that evidence is across the board. Very nice, like one sentence description that captures most of what we need to understand about how Bayes' theorem lets us make much, much more accurate probability judgments and fold in evidence and new observations. So that's the end of my 4 Introduction to Bayes' theorem lectures.